And let's unfreeze. There. So we have two functions, f of x and g of x, and we want h of x. So I'm going to do this both ways. I'm going to show you both methods, and then we'll see what happens, right? So the equation of this line, what's the slope of f of x? 2, right? We're going up 2 over 1, up 2 over 1, right? So this is the equation y equals 2x minus 4. Okay. What's the slope of g?
-1.
So, and then the y-intercept is 0, so this is just y equals negative x, right? So our h of x, which is f of g of x, f of g of x means you take g and plug it into your x in your f function, right? So f of g of x would be 2 times negative x minus 4, or negative 2x minus 4. So if I want h prime, what's h prime? It's negative 2, no matter what. No matter where you are, it's negative 2. So h prime of 3 would be negative 2, because h prime's a constant. Okay, so well done, Roman Legion. Right? Okay.
You got -2. Over there.
Oh, I looked at the green.
Oh yeah, no, that was the Asian. We got -2.
Okay, all right. So 2 groups got it. Well done. Okay. All right. Here's the thing. Every year on the AP exam, so just so you know, your AP exam has 45 multiple choice problems and 6 free response problems. The 45 multiple choice problems and the 6 free response problems are worth the exact same amount. They're each 50% of your score, right? One of those 45 multiple choice problems is going to test to see if you know chain rule. And most people understand the concept of chain rule. There he is. There. Okay. All right. Most people understand the concept of chain rule, which is if I have, guts squared, it's 2 times guts to the first d guts. Like most people, I work outside in, I multiply by the derivative of the argument. That's my chain rule, right? But a lot of students forget the actual rule. So most students know product rule, right? Product rule, f prime g plus f g prime. Like most students know the rule. Most students know quotient rule, f prime g minus f g prime over g squared, right? Most of us know quotient rule. Do most of us know chain rule? That one's a trickier one. It's actually not very big. It's just we don't drill it in a lot. So actual chain rule, if h of x equals f of g of x, then h prime of x is f prime of g of x times g prime of x. That's chain rule. So if we want h prime of 3, well, that's f prime of g of 3 times g prime of 3. I personally tend to find my inside first when I have to do one of these kinds of things. So this is f prime of g of 3. What is g of 3? Negative 3. All right, so what is this? It's the slope of f at negative 3 times the slope of g at 3. Now, the slope of f at negative 3 is the same as the slope of f anywhere on f because it's a line, right? So what's the slope of f? What's the slope of g? So what's our derivative? Negative 2. Right? Okay. Either way. Yeah.
You're just finding out how you got the numbers under the graph?
How I got these equations?
No, the ones like the...
Down here?
Yeah.
So h of x is equal to f of g of x, right? F of x is 2x minus 4. G of x is negative x. So f of g of x means you take g and plug it in for the x in your f function. So you end up with 2 times negative x minus 4 or negative 2x minus 4. That's f of g of x. And then h prime would be the derivative of that. Good. Other questions? This is called composition, right? Function composition. When you plug one function into another function. That's called composition. Okay. Today, logarithmic differentiation, 3.6b. Tomorrow, we're doing section 3.7, which is applications. Monday, we're jumping to section 3.9, which is also applications. Tuesday, we're going to do section 3.10, which is kind of a fun little topic called linear approximation. And then we're done with the unit. Now, we're skipping 3.8, not because it's a bad section, but because it's not on your test and it's not necessary yet. So what we're going to do is we're going to take the test. The test is a week from Tuesday. We'll start it a week from Monday. We'll finish it a week from Tuesday. Then that Wednesday is PSAT day. The Wednesday of the PSAT is the day that we are going to teach section 3H, or 3.8, which is really just a review from pre-calculus of exponential growth and decay. So if you are out on that day, there will be homework on PSAT day, and you'll just have to watch the screencast. But you get a 4-day weekend to do it. So anyway. Okay, but yeah, if you can, if you're planning on being out, try not to be out tomorrow or Monday, especially Monday. So, because those are 2 big application days. Yeah, sorry.
Wait, so it's not this Tuesday, but
A week from Tuesday is your test.
so like last Tuesday, the one yesterday, or
Okay, Tuesday was 2 days ago. It's Thursday. Yeah, and so no, not a week from last Tuesday. A week from Tuesday.
Got it. I was just not following.
Okay, yeah. All right. So, logarithmic differentiation sounds like differentiating a log, right? But you only use logarithmic differentiation when you have to differentiate a function that's not a log. It seems weird, right? A little bit. It's a weird name, and yet actually it's very appropriate once you see why. So logarithmic differentiation is a process where you use logarithms to simplify your function before you differentiate. Now, everyone in this room, if I asked you to actually find this derivative, you could do it, right? So it involved what rule? Chain rule and quotient rule, right? It involved quotient rule for sure. So you'd have some quotient rule with some chain rule mixed in. So you know, it'd be fine. You could do it. So you could find this derivative. However, wouldn't it be nice if there was a way to make it easier before you start, so you didn't have to do quotient rule with an embedded chain rule inside of it, right? That's where logarithmic differentiation comes in. Now, we can do anything we want to an equation as long as we do it to both sides, right? So what are we going to do to this equation? We're going to start by taking the log of both sides. When I say log, I mean natural log, always natural log. So I've taken the natural log of both sides. Why would I do this? Because on the right, what could I do now? I could break it up, right? I could totally expand that log. What I want you to do, now the left side doesn't change, right? Left side's still L and Y. On the right side, I want you all to take a minute and break up that log. Yes?
Can you use parentheses instead of brackets?
Oh, yeah. Yeah, I don't care. Grouping symbols are personal preference. That's fine. Make sure you put all your exponents in front. All right, are we ready? Getting some thumbs up, that's good. So first I'm going to do the natural log of x minus 2 squared, but where can I put the squared in front? So I could put a 2 in front. We all good with that? Now, what should I put here, a plus or a minus? Minus. Why minus? Because it's division, right? Okay. So now I have this ln of x squared plus 1. What should go in front of that? 1/2. All right. How are we? Are we all comfortable with expanding the log? Yeah. Yes. Okay, good, good. Okay. So now we're ready to differentiate. So I'm going to walk you through this derivative because some of you might not have done your homework last night yet, right? And might not have practiced derivatives of logs. After today, I think you'll be much more zippy with your derivatives of your logs. So first thing we're going to do is find, you got to differentiate both sides, right? So we got to differentiate the ln y. So before we differentiate ln y, let's see if you remember, Pranav, what is the, hi, how are you? Do you remember the derivative of ln of x? Yes. Yes, beautiful. Very good. It's 1 over x, right? The derivative of ln x is 1 over x. So the derivative of ln y would be 1 over y times dy dx, because it's not an x, right? 1 over y times dy dx. Are you all with me? A little bit of mini implicit differentiation mixed in there. All right. This guy, the 2 is a coefficient. Whenever you're differentiating a log, so what Pranav was saying is it's u prime over u. So you put your guts on the bottom and the derivative on top. That's all there is to it. So for the next one, I just draw a fraction bar first. Put the guts on the bottom, put the derivative of the guts on top. I like derivatives of logs. I think they're pretty snippy. So do you mind if I cancel these 2's? I mean, you don't have to, but for me, I would want those gone. All right, we're not quite done though, because we haven't actually said what's the derivative. We still have this like y sitting over here next to the dy dx, and we got to have dy dx by itself. So the next thing I'm going to do is multiply both sides by y. So I have dy dx equals 2 over x minus 2 minus x over x squared plus 1. And this whole thing is multiplied by y. So all I did, took this 1 over y and put the y over on the other side. Except, if we look at the original function, let's see if you remember. Is this original function defined explicitly or implicitly? Explicitly. It's y and it's all in terms of x. There's no y's in that function, right? It's all in terms of x. So our derivative should be all in terms of x. We shouldn't leave a y in our derivative. So, what could I replace the y with? Yes, the whole original function, x minus 2 squared over root x squared plus 1. So this is going to drive me crazy. So my final answer is going to be 2 over x minus 2 minus x over x squared plus 1 times, what is it, x minus 2 squared over the square root of x squared plus 1, because that's what y is. And there's my derivative. Yeah.
So on the test, you have to change y to time.
Now, personally, I don't think this made the derivative that much easier, right? It's not bad. It's actually pretty quick. I don't mind algebraic simplifying. If you had to do it using quotient rule, you'd have a lot of simplifying to do. Now, technically, this isn't really simplified because it's not one big fraction. But if you had to simplify this, then why are you doing logarithmic differentiation? Because this is a pain to simplify. So I just stop here and I'm happy, right? We're going to do one more like this, and then we're going to learn what you really need to use logarithmic differentiation for. Okay, these are like warm-ups. Are you ready? Okay, so I want you to try this one. Take a minute. So we take the natural log of both sides. Walking around, it looks like you guys did this really well. I'm going to rewrite the whole problem. You don't have to. I am just because I am. All right. I haven't done anything yet but put a log in front. Oh, whoops. I don't know why. I think I saw that too, and my brain said too. Thank you. Okay, good. All right, is that good? All right. So now I'm going to split up the log. By the way, before I start splitting up the log, I want to mention a very common mistake. So a very common mistake during logarithmic differentiation is students see the ln(y) and they're just dying to change it to 1 over y dy dx. So what happens is students will change this to 1 over y dy dx, but then on this side, they're still just breaking up the log. So what you've done is you've done the derivative of the left, but not the derivative of the right, and you've written a false statement. So be very careful that you don't differentiate until you are ready to differentiate both sides, right? So be very careful that you don't immediately jump to 1 over y dy dx here, because you're not differentiating it. So we have to just write it as ln(y) equals. Products go to addition, right? So this is 3/4 ln x plus 1/2 ln x squared plus 1 minus 5 ln 3x plus 2. Is that good? Good. All right. So now I'm ready to differentiate. Hey, what's the derivative of ln(y)? 1 over y dy dx equals 3/4 times derivative of ln x. 1 over x. Okay, plus 1/2 times, what goes on the bottom? What goes on the top?
2x.
Okay. Minus 5 times, what goes on the bottom? 3x plus 2. What goes on the top? 3. Are we all good? I start to feel better about derivatives of logs. They're pretty easy, right? Once you get used to them, they actually are pretty quick. All right. So now we have dy dx. I'm going to skip a step, and I'm just going to kind of clean this up. 3 over 4x. I'm going to kill the 2's. You don't have to, but I am. So we have plus x over x squared plus 1 minus 15 over 3x plus 2. And I have to multiply this whole thing by y, but what is y? The original function. And so the original function is x to the 3/4 times the square root of x squared plus 1 all over 3x plus 2 to the 5th. And then you just stop. Does that make sense? Okay, they're not bad. Now, that's one use for logarithmic differentiation, is allowing you to do a derivative, because, I mean, this derivative actually would be quite a pain to have to do by hand, right? Okay. So it does allow you to do a derivative a little bit faster if you have a complicated function. But the real reason we have log differentiation is so we can differentiate. That's so anticlimactic. This x to the x. Now, in your lives, I don't think you've encountered x to the x yet. So you've encountered x to a number, right? That's a polynomial. You've encountered number to the x, that's an exponential. But you've never encountered x to the x, which is still an exponential. But I like to think of it as like a super exponential. So x to the x grows super fast. It's like way faster than any other type of function, with the possible exception, of course, of factorials. But apart from that, x to the x is like the king of fast-growing functions, because if you have 2 to the x, you'd have 2 to the first, 2 to the second, 2 to the third, 2 to the fourth as you move along, right? Or if I had x squared, I would just have 1 squared, 2 squared, 3 squared, 4 squared. But if I have x to the x, I have 2 to the second, 3 to the third, 4 to the fourth, 5 to the fifth, 6 to the sixth, right? So my base is growing and my exponent is growing, which means I'm like flying super fast, right? So x to the x is a super fast growing function. The problem with x to the x is you can't use any of the derivative rules you've learned. You can only use the power rule, where you put the exponent out front and then subtract 1. You can only use that if your power is a number, right? That doesn't work if your power is a variable. You can only use the exponential rule, like the derivative of 2 to the u is 2 to the u prime ln 2, right? You can only use the exponential rule if your base is a number. It doesn't work if the base is x. So this guy doesn't fit any of the rules you've learned, and it doesn't have a rule. So how do we find the derivative of x to the x? What do you think we're going to use? Log differentiation. So first thing I'm going to do is just set this equal to y. So I'm going to write y equals x to the 2x plus 3. So that I have two sides of an equation that I can work with. All right, what do you think we're going to do? Take the natural log of both sides. Sue, hi. How are you? Oh, I'm doing just fine. Thank you for asking. Okay, good. So, Charles, how are you? I just wanted to ask how you're doing. Okay, Charles, what can I do to help my life right now? Not personally, but mathematically, right? With that 2, is there something I can do with the 2x plus 3? Ask a friend. Phone a friend. What do you think, Charles? Yes, it's an exponent. You can put it in front, right? So what we're going to do is we're going to take this exponent and we're going to move it in front. That's all we can do. So now we got to differentiate both sides. I want you to differentiate both sides, but I want you to be careful because the right side's going to require what? Product rule. Well done, Faith. Did you guys hear that? Product rule. All right, take a minute. See if you can find the derivative of both sides. No, there's an x in it. That's okay. As soon as you say the letter x, it's not a constant. Yeah.
Two times 1 over x plus 2x plus 3. So we differentiate 2x plus 3. Find the derivative of 2x plus 3. We're not allowed to negative exponents, fractions, and complex fractions, and then that's it.
And you have to simplify all three.
So it's
And
2
2 ln of x
That's what?
plus 2x plus 3
It's not that bad.
1 over
Just 2 right?
All right, class. What's the derivative of the natural log of y? 1 over y times dy dx. Good. All right. Don't start putting 1 over y dy dx every time you see the letter y, right? It's natural log of y is 1 over y dy dx. Okay. All right. Product rule. What's the derivative of 2x plus 3? 2 times ln x plus 2x plus 3. What's the derivative of ln x? 1 over x. All right. So dy dx equals 2 ln x plus 2x plus 3 over x times y, but what is y? Times x to the 2x plus 3. And there's your answer. Okay. Yay! Yes. All right, and there was much rejoicing. Okay. So it's time for a brain break. Okay. So one last note about logs. I'm going to spend like 3 minutes explaining something that's for a concept that's like super, super simple. But I want to go a little bit deeper just so you understand why this concept is super simple. Do you want me to show you the simple concept first and then explain, or explain first and then show you the concept? Concept first. Oh, I'm hearing quite a variety.
Concept first.
Concept first. Okay, here's the concept. It's okay. Don't worry. You'll get the explanation either way. So the derivative, if you ever have a derivative of a natural log with an absolute value around the argument, all right? If you ever see, and the College Board loves these, so if you ever see a derivative of a natural log with an absolute value around the argument, you do not have to write it as a piecewise. The derivative is exactly the same as if the absolute value wasn't there. So the derivative of this, what would go on the bottom? 5x minus 2. What would go on top? 5. Done. Okay? So a derivative with an absolute value in the argument of a log is the exact same as the derivative without the absolute value in the argument of the log. Why is this? Here's your explanation. So if we have y equals ln x, right? So the graph of y equals ln x looks like this. It's this little swoop, right? We've been talking about this. The derivative of y equals ln x is 1 over x. 1 over x looks like that. Do you see a problem? We have derivative values for a function that doesn't even exist, right? The whole left side of the y-axis on the graph of y equals ln x is just space. There's nothing there. So how can you have derivative values for a graph that doesn't exist, right? Technically, the derivative of y equals ln x is 1 over x with a domain restriction of x greater than 0. We don't make you write the domain restriction, and the College Board doesn't make you write the domain restriction. Yeah, but technically, the derivative of this is this with a domain restriction, right? This is truly, actually, the derivative of y equals ln absolute value x. The natural log of the absolute value x, if we were to graph it. All right, ln of x, so absolute value is moot when x is positive. It's the same as ln x, right? So for all the positive x's, it looks just like ln x. Let's think about the negatives. When we take an absolute value of our input, that means that the ln of negative 3 would be the same as the ln of 3. And the ln of negative 5 would be the same as the ln of 5, right? What you end up getting is you get this lovely reflection over the y-axis. So you end up with that. as the graph of y equals ln of the absolute value of x. This is the derivative of this. And I want to just make one more slight connection here, okay? Quick connection. The derivative for all negative x values is below the x-axis, which means all these values are negative. When all of your derivative values are negative, it means all your slopes are negative, which means your graph in this region should be going down, right? Decreasing, not negative, but decreasing, right? So negative slope means the graph is decreasing, okay? Here, the slopes are positive, graph is increasing, right? Increasing. Does that make sense? Okay, they're mirror images. These, believe it or not, are just reflections of each other, right? And these are reflections. You'll get the same numeric values of slopes, just with opposite signs. Okay. So anyway, so all that being said, that's just to tell you that if you ever have a derivative of log with an absolute value, you can just ignore the absolute value and just do a derivative. Okay. All right, one more thing, which is an AP practice problem before course starts. So 2015 number 6, which my link is not working, but I can pull it up from scratch. All right. I've had good technology today. Like everything's worked all right, so that's good. Yeah. Anyone can access the College Board web. You already should all have a College Board access, right? You should be able to access anything you want on the College Board. So, yes, all past, yeah. All right. All right. Okay, so this is from the 2015 exam. This was the AB exam, problem number 6. I'm going to read it to you for a minute, and then I'm going to give you your instructions. So consider the curve y cubed minus xy equals 2. It can be shown that dy dx is y over 3y squared minus x. They give you the derivative, right? Why do they do that? Probably because they're worried that everyone would get it wrong and then they'd have to grade all this craziness based on your wrong derivative. So they give you the derivative. Part A, write an equation for the line tangent at the point -1, 1. Easy peasy. Part B, find the coordinates of all points on the curve where the tangent line is vertical. How do we know, what do we know about a vertical line? Tell me anything you know about a vertical line. The slope is undefined, right? The slope is undefined. So if this is my derivative and derivative gives me slope, how would I know when the slope is undefined? When the denominator equals 0, right? Something that causes you to divide by 0 makes you get an undefined slope. So you're going to have to set the denominator equal to 0. Now, there's a problem when you set that equal to 0 in that you have 2 unknowns and only 1 equation. You're going to need to find a second equation, and it's on the board, with those same 2 variables, and do a little substitution, okay? Nice little review of systems of equations, so it'll be fun. All right, and then the last one is find the second derivative. So I want these on your whiteboards. I'm going to give you 5 minutes to do the whole thing. Go.
Go.
Okay. Okay, the first part was worth 2 points. You got a point if you found the slope was 1/4 by plugging in the number. And then you got another point for writing the equation of the line. Anything equivalent to this is fine, right? Anything equivalent is fine. I think every single group got it right when I was walking around. It looked like you all did. So well done. All right, for the second part, you had to set that denominator equal to 0. That was worth a point, just for showing that you set the denominator equal to 0, right? So you get a point for writing that down. Then you get a point if you found an equation in one variable. Now, personally, what I would do is solve this for x and say, oh, look, x equals 3y squared. And then I would go to my original function and replace the x with a 3y squared. So I know it's weird that this is derivative and this is original function, but it's the same x's and the same y's. So they have to, everything has to hold true. So yes, you can substitute from the derivative into the original function. That's okay. So we've got this. So then you end up, when you do some algebra, you get y equals -1. So any equation that was in terms of one variable, now if you solve for y, it's a much uglier equation, but you could, right? So any equation that was in terms of one variable got you a point. And then your final answer was 3, -1. So well done. There were several groups who got it, so good job. There were some groups in first period who got this right here, this x equals 3y squared, and didn't know what to do, so they guessed 0, 0 because 0, 0 works, right? They started just doing guess and check and kind of guessing random pairs of numbers that happen to work, right? There's infinitely many pairs of numbers that will work with this. You can't do it that way, right? So 0, 0 happens to work, but if you plug 0, 0, come on. Where'd it go? Here it is. If you plug 0, 0 into your original equation, into this thing right here, right, the original equation, plug 0, 0 in and see what happens.
It's not a point.
It's not a point on the function, right? It may fit that derivative requirement, but it doesn't work if it doesn't exist on the function, right? So you can't just guess randomly and hope for the best. You have to actually do some math, right? Okay, so that was part B. So part B was worth 3 points. If part A was worth 2 and part B was worth 3, how many points was part C worth? 4 points, because every free response question is how many points? 9 points. Now, normally, how much time do you get for a free response question? 15 minutes. I gave you 5, right? So you didn't have enough time, but that's okay. So for the third part, all you had to do is find the second derivative. It was a little messy. No, you don't have to simplify, but they asked it at a number, so you had to plug in the number, right? Okay, so you got a point if you had your second derivative, right? That was, 2 points. So this guy right here, that guy, 2 points. Then you got a point if, when you're plugging in, if your dy dx's were equivalent to a fourth, right? If you substituted your numbers in properly, and then your answer, like either of these is fine. So anyway, so a point for the final answer. But 2 points for your second derivative, right? Okay, so I'm going to shut off the recording, and then we're going to talk about core.